Good morning, good afternoon, good evening, everyone. We are having today a webinar on cost model for fusion power plants. This is a project in which we have been working for the last couple of years in partnership with Gulder Scientific. We founded this element as an important element for fusion, and this is now the time where our first version of the model and the connected application is available. So we want to offer all the fusion audience this tool to be used and of course to be improved over time. Next one, please. So the first thing that I would like is to introduce the team who made that possible. And I would like to mention first Simon Woodruff, founder of Gulder Scientific. He has a strong background in the cost model analysis. He's well known in the community for that. And he and his team was partnering with us to be able to develop this model to improve it because we started from an existing one and he will provide all the information. And Alicia Durham, who is part of his team, and has been focusing on the safety aspect. She will go into more details about that. I would like also to introduce Chris Rastak, who has been working hard, making the application possible. He's a senior software developer from Rastak Tech. And last but not least, Jay Brister is managing director of Blue Sky Nuclear, a person with a very strong background in nuclear technologies and who has been working together with Simon, Alicia, and Chris to have everything ready and who is part of our usual activities at Clean Air Task Force. Next one, please. So this webinar, the intention is to make it very interactive and to explain what is behind the model and how to use the model. So the first thing that we will have is an introduction to CATF and what CATF does in particular to fusion. And then I will give the floor to Simon to talk about the model, how the model was set up, on which previous works it was built. We will make a special emphasis in safety and hazard, and this will be explained by Alicia. Then we'll have an introduction to the application, how to make it work, where can I find it. This will be done by Jai. We will have a live demo with an example, so you will have the chance to see how it works. It's very friendly, user-friendly. This will be done by Chris. We will analyze the output of this model, which results we get, which is the meaning of these results. That will be explained by Jay, and then we'll have a little bit of time for Q&A. A couple of practical things. The first thing, this webinar is being recorded, and everyone who has been registered will receive a copy when ready. Another point is that we are always available for further questions, comments, etc. As I said, this is the first version of this application, the first version of the model. It will not finish here. We will continue improving this work. We want to include more data and to make it as accurate as possible. So all your feedback, all your comments will be really, really welcome. Next one, please. So starting from the beginning, what is CATF for those who don't know, and what is CATF doing on fusion? Next one, please. CATF is a non-profit organization that was founded in 1996, so already 30 years. Started focus on US, then the focus expanded, and in particular the fusion program is a global program where we work in US, UK, Europe, and Japan mostly, but not only. The mission of Clean Air Task Force was focused on achieve reduction in smoke, air toxics, and carbon dioxide from US. That was expanding when CATS was expanding, and now, and I particularly like that mission, is to broaden the mandate devoted to science-driven solutions or solution-oriented approach to combat climate change and environmental degradation. And fusion fits very well here because we need new technologies to have new tools to fight to climate change and environmental degradation. And fusion is one of these tools. We started the program 3 years ago in 2023, and Again, as I said before, the work that we are presenting here is one of the things that we have been working since then. Next one, please. So what else is CATF doing? We have a number of programs, starting from methane pollution, in also advanced nuclear, super hot rock. We have a strong teams in policy in US, in Europe. We have a program on hydrogen. We have on carbon capture, super energy and climate innovation in Africa even. So as you can see, it's a great ecosystem for the fusion team to be part of. We benefit of all these synergies, and it's clear that the focus of Cleaner Task Force is to find better tools to make energy accessible without degrading the environment. Please, next one. So, going a little bit into fusion. What is fusion doing? Which is the fusion program role in CATF? What we do is to push toward commercialization. This is our focus. We want fusion to become real, a real source of energy for the mankind. And for that, we have the flexibility of team up with key stakeholders from the public and the private sector, including also the academia, policymakers, etc. So we want to have the input and the contribution of everyone to make it happen, to make fusion happen. We are focusing in a few major topics. We'll show you later where the cost is included, but just to give you an overview, we are working on regulatory framework for fusion, supporting the development of appropriate fusion energy policies and standards, addressing some supply chain challenges, and providing visibility to fusion energy as a part of the clean technology sector. Because again, fusion is becoming a real thing and needs to be discussed at that level. We have set up a number of international working groups, and the work that you are going to see in this webinar is the result of one of those. One of these international working groups that was run by Simon and his team. It was on cost analysis and techno-economic modeling for fusion. Is an activity that I say we want to keep it, and we want to get more data, get more knowledge, introducing into the model, into the application, get better and better over time. We also have code and standards for fusion system and artificial intelligence assisted database for fusion materials, among others activities. Next one, please. As you can see, this activity on cost model is included in our pillar 2, de-risking strategies, and we understand that to de-risk fusion, we need to identify generate an economic cost analysis. We need to identify which are the major drivers in terms of cost in building a fusion power plant. We need to have this tool to compare and to learn where are the key elements, which is the impact, what happens if I change the parameters of my machine, at least at a high level. Next one, please. Before we move really to the model, I want to alert, I will say, about two things. Don't expect from that model to have a real levelized cost of electricity. Right now, we don't have that information. I don't think many people will have that information. So the use of that model is two. The first thing is to have a clear structure of the cost of a fusion power plant, and Simon will go a little bit deeper on that. And the second is to have elements to compare, to identify major drivers, to see what happens if I change the radius of my machine, if I change the power of my machine, and to have relative figures, not absolute values. Again, the idea and the ultimate goal of this program, of this piece of work and the application is to have enough information, enough in terms of number of parameters and accurate enough to be able to produce a levelized cost of electricity, which is real. But right now, we are far from that. So don't take it as a absolute value, it's a relative value. The added value of this program is to have this understanding of how the cost has an impact and the structure of those costs. And I will see the importance of including this module on safety, that before was not included. We want to get better and better, more accurate over time. But this is, I would say, the version 0, and we will build on that. For that, it's very important your input. So be proactive. All comments, questions, suggestions are very, very welcome. And now, please, Simon, the floor is yours.
Thanks, Anna. So this started in 2011. In fact, I went to talk with investors in Palo Alto, and I got meetings with some of the lead investors, and they wanted to know the two things. They wanted to know more about fusion, but they wanted to know what the levelized cost of electricity would be from a fusion concept and what the total capital costs would be. So they universally they asked two questions, and this caused me to take a bit of a shift in career and pursue these two questions. So I started working with the Aries team in the form of Ron Miller and Leila El Gabali. And so we started rewriting the Aries code in a more general way. So we wanted to understand what the levelized cost of electricity was for our fusion systems that we're designing for super compact systems. And we published a series of papers, and in 2017, ARPA-E invited us to participate in a study with Bechtel. And Bechtel brought in as the engineering procurement construction company that could review the balance of plant and help us with the whole power plant costing. So we got a calibration point in 2017, and then the entire modeling effort evolved over a series of years subsequently. I'll mention that in a second. But the methodology has been pretty much the same throughout. I mean, we start with a power balance, we get into the radial build, and then we wrap around a fusion power core, the bioshield, and the containment building, and all the other buildings on the plant until we get to the site boundary. So we start at the first wall and go to the site boundary in terms of costing analysis. We realized early on that if we were to apply this methodology to a wide set of concepts, everything from IFE, magneto-inertial fusion, magnetic fusion energy, we would rely on the teams themselves to produce the physics modeling. So while we developed physics modules early on, they were all stripped out immediately and replaced with the physics modules that the teams preferred. So we were starting with a power balance and ending up with the capex. And the first study in 2017 didn't go as far as LCOE, as Sahila mentioned. It was quite uncertain, but the fidelity of the analysis has evolved over time, and we've done everything now from first of a kind to nth of a kind. Most of the analysis that we're releasing now under the Clean Air Task Force is for nth of a kind. Next slide. So the idea has been always to form a very standardized costing methodology. So we built on Aries, but we have drawn on various other standard cost of accounts from IAEA to Gen 4 and more recently EPRI have adopted the same cost of accounts for performing the costing analysis. But that's been embedded in everything that we've been doing from the outset, is to think how to do a very standardized costing. So if you've seen the reports, they're all the same. They all have the same sections. They all have the same major cost account categories. And the methodology that we pursue in the cost accounts is always the same. And we state what is in the cost account, what are all the subsystems that we're costing, and then we make a calculation based on a reference or a cost basis, and we draw upon a whole range of different reports for those cost bases. So over the years, we've gone from the Aries top-down costing through to more recently doing everything bottom up. So that means we calculate the cost of the individual components and build up the system. And we do that principally for the major cost drivers. We go into excruciating detail with those systems that are the most expensive and impact the costs the most. So that's where we spend most of our effort, is understanding those major cost drivers. Next slide, please. So what do the cost accounts look like? They're, like I say, they're super standardized. There are multiple references, and we've deliberately chosen the IAEA cost accounts because they're super well documented and were adopted by Gen 4 in 2007. So yeah, we deliberately chose those so that we could draw on from the major source of literature. There are books published. Jeffrey Rothwell, for example, has a textbook on calculating most of the major cost components. But most of the time is spent when we're costing fusion power plants in the 20s. So cost category 22 is the power core, or the plant equipment that is directly fusion related. So we dig down into that in some detail, and we draw on the prior art. We bring the teams together. And often our costing analysis has been the first that has been performed for the team. And we go through a down selection of materials on the first wall, the types of blanket, the different types of breeder blankets that we could be considered, what types of shielding, and then we get into the details of the magnet build, or the laser build, or the pulse power systems that are used for MFE and IFE and magneto-inertial fusion. So yeah, so over the years we've worked with most of the private fusion companies, and we've been able to tailor the analysis to each and every fusion concept where that information exists. So so those are all pulled together. It's several thousand lines of Python coding now, and but it's standard. There's a common thread to all of this, and that's the cost of counts. Next slide. Yeah, so this just shows the flow of the calculations. We start with various inputs. Often the system has one module. Some systems have multiple power cores in the same power plant. But things like that, those are the sorts of things we capture initially. And then we get into the power balance, and we take verbatim what the teams are actually proposing. I mean, we don't get into the review of their physics modeling. So the starting point is the fusion power. And then we then do the radial build. So we go from the first wall all the way out to the site boundary. And we've done this now for all fuel types, and looked at most of the blanket configurations, and looked at most of the magnet builds and the different types of lasers, excimer lasers or DPSSLs, and looked at various different pulse power scenarios. So there's a large amount of information that we pulled together, and these are now made accessible through the Clean Air Task Force web portal. And there are 3 different flavors of the code for MFE, IFE, and magneto-inertial fusion. And there are ways to get into that and to change things and set things up such that they reflect a particular scenario. So that's the background. The future is interesting. We are looking to do more with simulations, and so we're using the framework, but launching simulations from the framework, and that produces a much higher fidelity of analysis. So there are interesting things that are coming up. And there's an awful lot of information that is coming out of the Clean Air Task Force, of the international working groups for materials and for safety, that is being generated on a month-to-month basis, that is being captured now in the Clean Air Task Force branch of the code. And Alicia will talk a little bit about some of the safety aspects that are being captured right now.
Hello, everyone. Thank you, Simon. As you said, I'm going to talk about how we thought about implementing the safety aspects into the costing code. So yeah, let's start. Next slide, please. So as Fusion goes towards commercialization, we started thinking about how to capture the safety costs as they were more prominent, and the UK and the US were starting to think about the regulatory framework for fusion and how to license power plants. So to do this, we decided to engage with the industry and all the stakeholders and have active discussions with people that were involved in these decisions. So we participated in meetings and working groups. So we interfaced a lot with the Clean Air Task Force's Fusion Safety and Regulation Working Group, which gave us a lot of information that we could work on. And we also attended an IAEA meeting, and this allowed us to understand the general feeling and how safety was going to be considered for fusion and how it was going to be regulated, and therefore how we should cost it. Next slide, please. So the way we actually went about this is that we listed the type of hazards we had for fusion power plants, and we mapped them out onto the cost categories. Then we assigned this hazard category index, which was developed by Patrick White and his PhD, who is the leader for the Clean Air Task Force Fusion Regulation and Working Group. And he basically developed this index, and it gives an idea of how much the hazard has a regulatory and importance, and how high the consequences of a hazard can be. So this index gave us an idea of how much cost would be associated with it and how much it would influence the overall cost of a fusion power plant. So we got the hazards with the highest index, and we translated them into a cost and included them in the code. Next slide, please. So just to talk about an example, this one is quite relevant, and it's both in the MFE and the IFE code. Basically, we have the capability of calculating a site boundary given tritium inventory for the fusion power plant. When we first started thinking about this, we were thinking about using maybe Patrick White's data. Again, Patrick White is the leader of the Clean Air Task Force Fusion Safety and Regulatory Working Group, and he looked at this in his PhD thesis. But we quickly understood that a worst case scenario wouldn't be representative of a real situation, and therefore wouldn't capture the cost as well. So we decided to use a maximum credible release analysis based on a study from Lawrence Williams, who is also a participator in the Clean Air Task Force Safety Group. And basically, this maximum credible release scenario consists in a scenario where the weather conditions are not as adverse, and also it assumes that you have some systems in place to mitigate your release of tritium in the event of an accident. So it goes through the ventilation stack in your fusion power plant. So we can go ahead and look at the code and how we capture this cost. So in the next slide, please. So the way the code and the calculation actually works is that it takes as an input the height of the ventilation stack of the fusion power plant, and it selects the data from Lawrence Williams' study. It performs a polynomial fit, and that will allow us to predict what type of site boundary we need. So it takes as an input also our tritium inventory. It assumes 10% of it gets released through the ventilation stack, and this gets translated into a dose. And based on the doses for the dose limits for evacuation and sheltering, we calculate how big a site boundary would have to be to avoid evacuation or sheltering. So that site boundary then serves as a radius to calculate an area and how much land we actually need for the site, and it gets translated into a cost. So this is an example of how we implemented one of the safety aspects into the cost model. Going ahead, into the next slide, please. We also talked about policy aspects, so insurance and licensing, which are some novelties in this code. And we thought insurance was important because the UK government did determine that a liability regime was necessary, and through discussions with the Cleaner Task Force working group, safety working group, we understood that we should capture this cost. And the way we did this was by adapting the premium from fission into fusion, by weighting it using this level of safety assurance, LSA, from an ARPA-E study. And this gives us a range in which our premium would be for fusion. This is it's very general. It needs more work for sure. It's a bit of a guess, but it's a start to start thinking about this, and it starts the dialogue around these costs and what it will be. And the same goes for licensing, which is in the next slide. We had a discussion about how this would be considered as a cost, and we understood that probably the regulatory work hours would be the cost driver. So we did get the Advance Act hourly fees and also some hourly fees from the from HSE, which is the UK regulator, and we put them in the code to capture the licensing fees. So this part of the code does select if your fusion power plant would be in the UK or in the US, and that's an input. So this is how we captured some of the costs for safety. There's other aspects, but these are probably the more relevant and new ones. So that's all. Thank you.
Hi, folks. I'm going to walk you through just what you're going to see when you get over to the app and begin to interface with the app. So, Jack, let's go to the next slide, please. So here's a QR code, and you can see the web address there for the model itself. Let's go ahead and go to the next slide, Jack. So when you get to the site, this is what you're going to see. Again, just fusioncostmodel.app. It's easy to remember. And when you get to the homepage for the cost model, next slide, Jack. When you get down to the bottom, you'll see a getting started button here to get you into the application. And again, as we mentioned earlier, this is our first iteration on the model. We're looking forward to everyone getting involved and continue to provide feedback for us for improvement of our model over time. So once you get into the model itself, so click the Get Started button, and it'll take you through a couple of account setup pages there. So you'll get your email address in, password, and from that point, it will take you into the model where you can begin to actually create a new project. And Chris Rostad is going to walk you through that. But before we turn it over to Chris, you go to the next slide, Jack. Just wanted to kind of let you know what will be configured today as we go through the model, just to give you a frame of reference. So Simon talked through a lot of the variables that you can configure in the model. And so just as a kind of historical reference here and for the replay and refresh of this, when you look at this again, just wanted to make sure we had this captured so you can kind of see the basic components that we will be walking through. So construction time, configuring the power aspects of the machine, the blanket aspects of the machine, and there is variability on materials in the model as well. We're going to just use the default values that we have set in the model for today's example. And also today, we're just going to go through a magnetic confinement example just for the sake of time. You can see when you get into the application itself, you can go in and actually create other technology approaches as well, as Simon mentioned, and the technology dependent and technology related configurations will be in those as well for you to be able to work through and manipulate to get the output. So with that, I think we're ready to turn it over to Chris, and he will walk us through a demo.
All right, can you see my screen? Great, cool. Right, so Chris, principal developer on the Fusion Cost Model web app, and translating the work of Simon and crew into the PyFecons library. So Fusion Cost Model.app, this is the web page. And when you get here, you'll get to the landing page and scroll through all the various information. There's a link to the GitHub repository, which houses...
Chris, sorry to interrupt you. It seems we can hear you like far, far away. If you can get closer to the microphone or so, it would be easier. Thank you.
Oh, sorry. Okay, can you hear me better?
Much better, thank you.
Okay, thank you. All right, I'll speak up a little bit more. So yeah, as I mentioned, cost model, you can navigate here in your browser. The bottom here, we have a link to the PyFecons library. This is the open source library that powers this web application. It loads it as a reference into the application, and that's what does the cost calculations and the report generation. So after you do the sign up and password creation phase that Jay talked about, you should be able to get to this page, projects page. You can create a new project for a fusion reactor. So MFE reactor. Then machine type, you can go MFE, magnetic fusion energy, energy conversion, turbine, fuel type, DT. So after creating the new project, voila, now we can go and create a configuration. So configuration is the inputs for a cost calculation and report generation. So our MFE vector, as most of the values, you can just use the defaults for just playing around with the code. Little tool tips will tell you what exactly things do. So we will up construction time to 6 years. You can use sliders or type in values, set the values. And so in the cost model, we have an option to include or not include the safety and hazards analysis. It's quite new and recently added, but it takes the work that Alicia has done and puts it inside this PyFecons library that then gets used for report generation when this is selected. So I'm going to select that for now for demo purposes. And then that gets us to the variables from the safety and hazards configuration. I'll select United States. These are the same variables that Alicia showed earlier in her Colab code. So the Colab code is kind of the base for what got inputted into the model that powers this part. So next, then the power configuration, very important for fusion reactors. I will go down here and set the TF coils power to 12 megawatts. And up this PF coil to 6. All right, next, then the blanket configuration for the radial build. I'll do tungsten first wall, solid first wall with a liquid braided blanket type. Primary coolant will be lead lithium. We will select none for secondary coolant, and beryllium for neutron multiplier. Finally, FMS for the structural material. Of course, we got the tooltips. You're confused about what these are. And finally, these are some of the material configurations, cost of various materials. Can hide those for now. Now, we will be generating the report here. So it's doing calculations and running the LaTeX commands for generating the report. Think. Right. There we go. Cool. So this was created for an MFE reactor. Probably should have put report there. You'll have the inputs as human readable form in these drop downs. And finally, we can download the report and the inputs. And if you come back to your project, you'll be able to see configuration in there. And in your dashboard, you'll see the project. So you can go through, do the same thing for IFE, and generate another report. All right, so that concludes the demo of the fusion cost model. I'll let you take over, Jack. And Jay. Jay will go through now the report that gets generated.
Thanks, Chris. So I'll just pull out some highlights out of the model to kind of show you how the data is going to be presented in your report. So let's go ahead and go to the next slide, please, Jack. Next slide. So again, just a little repeat from what Simon said a little earlier. And when you get your report, you'll see that there is a bit of a precursor in the report as well that will talk you through some of the modeling basics. And then depending upon whether or not you include or don't include safety, there'll be a precursor to the data on safety if you include that into your configuration as well. And again, just highlighting the standardized cost categories that'll be reflected in the report. Category 10 through 60 will be highlighted. So next slide, please, Jack. So what you'll get in your report when you kind of get into the meat and potatoes of the output is a cost accounting structure table, where, as Simon said, we really break down the costs first at a high level to look at total capital cost, and again, just across the high level categories. And then with increasing detail, kind of as we move across the page here, you can see that under the direct cost, underneath direct costs, you've got an expansion of cost elements that add into that. And then when you really delve into the machine itself, another level of detail there. So Sahila mentioned when you configure and run a cost model, when you get your analysis, it's a primary tool to allow you to see the significance of how direct costs tie into the overall cost of a fusion machine. And then within direct costs, really beginning to see at a component level, system level, which of those are really major drivers for your costing as well. So what we've done, in addition to just the tabular output of the data, we've taken these three broader categories: total capital cost, direct cost, and reactor plant equipment cost. And if we'll kind of go through the next couple of slides here, Jack, just kind of show you where you can see graphically kind of how that cost begins to break down. So you can kind of see, for example, in this run, 75% of the overall costs are in a direct cost of the machine. And we go to the next slide, Jack. When we kind of delve into direct costs, you can begin to see here again how major components there feed into that. So the fusion machine component there is a big driver in your cost as you look at that. And then when you kind of get into the overall plant equipment, we break that down on the next graphic. So this is the kind of tool you can see so when I'm looking at my machine, when I'm looking at how do I configure the various components, you can see the level of significance of the impact on cost to how you're designing a machine as you alternate your configurations, or you want to understand how cost is affected by changes in your systems or power, or either your first wall and your blanket designs. There's some direct outputs from that as well that give you this visualization to understand that as you work through this. And then, as Sahila mentioned earlier, go ahead and go to the next slide, Jack. Your last output at this point is a preliminary kind of LCOE analysis to kind of give you an idea of where electricity is going to fit with the configurations that you're doing. And then, as we said, as we progress through this over time, with input from the industry, with input from all of you, is begin to refine the inputs, refine the credibility, and progress at the point in parallel with the development of the technology to get to an LCOE that is more realistic. But of course, that is going to be very, very time dependent and dependent upon the maturation of the various fusion concept power plant designs as we progress through this as well. So I think that's a quick output of the model output. I think it's going to be a 4 to 5 page report that concisely provides you all of this that you can begin to use and manipulate for your own purposes. So I think that's it for me, Jack.
Thank you very much, Jay, and thanks for the presentation. I hope it is clear. We have a few minutes for Q&A. I would highly appreciate it if someone has some doubt or how to get into the application or something that has been missing during the presentation. We have a little bit of time, so we have no problem in going back to that and check it again. If not, please type in the chat. I will try to. There are a number of questions already coming, so I will try to select the I wouldn't say the most relevant, the ones that I can see, and the speaker will answer. But before we move to that, just a reminder: the webinar is recorded. It will be sent to all participants, and we will attach also the report corresponding to the simulation done in the live demo, but also we will attach a report on inertial fusion in an inertial fusion machine. So you have both as a reference. We have shown only the magnetic confinement machine for simplicity, but the report, the application offers the possibility also to simulate inertial fusion machines. Over time, we will include more features and we will make it more comprehensive. But as I said before, step by step, we want to build this application to make it useful for the whole community and the reference application for cost calculation. So I have a question here, which I think is quite interesting. Where from sources are the data to the application uploaded? Are they actualized? So Simon and Chris, please. Should I repeat it, the question?
Yeah, no, I see it.
Okay.
So the code is available in a GitHub, and if you go to woodruffscientific.com or navigate to the app website, then there's a link to it.
Yeah, I can chime in a little bit. I was having a hard time understanding the question, the sources part. But So the library powers the calculations, and then Clean Air Task Force has a deployment of a web application that then takes the inputs and processes them. And so the history and everything is in a database under Clean Air Task Force.
We have here, sorry, thank you very much. I think we move to the next one. We have here a long question. I will try to summarize a little bit. And we have a colleague who say, for methodology, how do you deal with plus minus uncertainty in the case of fusion plants where there is even less historical baseline that for example, large light water reactor or plants? Simon, you want to answer?
Yeah. So we're talking about plasma uncertainty. So we don't do any plasma modeling per se. We start with a power balance. So there's an aspect to this which is different from other systems codes where often the plasma physics or the engineering modeling is built in. We're providing a costing framework that basically goes through the chart of accounts that have been standardized and established by the IAEA and Gen 4 and others, and provides a cost basis and a calculation for the major cost drivers. So it's a bit different from other systems codes. So we're not really dwelling on plasma physics per se.
Okay, thank you very much. I think we have a little bit of time for one more coming, which is more into the report and a little bit of how to improve things. It says, so the power accounting table show a high scientific Q, but a much lower engineering Q due to recirculating power requirements. From a commercial perspective, which subsystem offer the greatest level of leverage to reduce recirculating power and improve the net electric output? And how realistic this improvement in the next generation of fusion plant can be? I think this is a little bit like to foresee the future, but the role of this recirculating power, I think it's important to highlight. Please, which are the elements that could improve over time to be more efficient into that aspect?
Yes. So recirculating power goes to power to magnets or to input power heating. So any gains in efficiency for heating systems or current drive systems, or any reduction in power that goes to the magnets, for example, in an MFE system. Those are the dominant drivers of recirculating power fraction. So HTS obviously makes a big difference.
Okay, we have, and I think that should be, if not the last one, the last two ones now, from our colleague and contributor today for Michael Stanstorff. How are you handling the cost of hazard mitigation for beryllium?
I'm not sure that we are, or are we?
Simon,
for
Alicia, this is tricky.
Thanks, Mike.
This is why we need everyone in this international working group, because it's where we discuss particularly these kind of tricky questions.
Yeah, I don't think we're including those at the moment. We looked at some material costs and material degradation, but there's a lot of work to do with the integration of the rest of the model in the material libraries, and so we didn't manage to include them, but we did look into them, and that's one of the parts we're still working on. They're not included at the moment.
This is a clear example why the levelized cost of electricity is not real. We can use this model so far to have an idea of the structure of the cost and to have a relative comparison, not an actual one. We will have to refine and refine, and this is a good example. I think we go to the last question. Also, can we extract both the cost of construction and the cost of full operation?
Cost of construction and the cost of operation. Is that the operation and maintenance costs? So we do it's an nth of a kind costing. So we're looking at the costs after learning has been reaped. And we include operation and maintenance costs for nth of a kind, but we're not including first of a kind construction costs per se.
Okay, thank you very much. I will say the floor is still open for question, comments, contribution. As we say, this is the first of a kind of a model for cost. It needs to be improved and incorporate all the new information that is going to come in the next year. The final goal, the ultimate goal is to have a real levelized cost of electricity, but in between we will be improving. And all your suggestions, inputs, information is really, really welcome. This is to help the community, and we rely on the community to provide information. So it's a teamwork. So thank you very much. And again, you will receive all the material, all the information, play with the model, and send us your feedback. If you want to join the working group, send us an email. All the email for contacts are in the presentation. And thanks for attending this webinar. And thanks to the speakers. Thank you very much. Bye.